A magnetic field has a direction, so we represent it with field lines to show this direction. For a stronger field, we draw the field lines closer together, and for a weaker field, further apart. Suppose I put a 2p piece in each field, perpendicular to the field lines. It makes sense to say that there is more field in the 2p piece in the strong field than in the one in the weak field. So how much is there? Well, we calculate the amount of field in each 2p piece by multiplying the area of the 2p piece by the strength of the field, which remember is B, the magnetic flux density. The name we give to amount of field in a given area is magnetic flux. This is a very old term that came from when people thought the magnetic field was flowing, and people still talk about the amount of field passing through a given area. Magnetic flux can obviously be measured in Tesla meters squared, but also has its own unit, the Weber, where 1 Weber equals 1 Tesla meter squared. However, we need to make this a little more complicated because you can see that if we tilt the 2p piece, not as much field is in it or going through it, however you prefer to think of it. There aren't as many field lines going through the coin. We correct our formula to take this into account by adding a cos theta to give us the area perpendicular to the field. Now, slightly confusingly, this theta is the angle between the field lines and the normal to the area. Needless to say, always draw a diagram to make sure you get the right angle. So if we move a wire through a magnetic field, we can work out how much magnetic flux the wire has moved through. Let's say the wire has length L and we move it a distance x. Then the area it sweeps out will be Lx, but let's just keep calling it A. So if we move the wire perpendicular to the field, it will move through BA, because the angle between the field and the normal will be 0, and so cos theta will be 1. If instead it moves parallel to the field, it will not move through any flux, and so phi equals 0, theta equals 90, and cos theta equals 0. And if it moves at an angle, it will move through phi equals BA cos theta. We often refer to the magnetic flux a wire has moved through as the change in flux experienced by the wire. If we had a coil of wire in a uniform magnetic field, we could ask, what's the magnetic flux inside this coil? Here's an example, and we can calculate using the values given, where here the coil is perpendicular to the field. Now, if we add more turns of wire to the coil, then as far as the wire is concerned, it's now enclosing more area. So let's say we made this coil have 3 turns. Then the area enclosed by the wire would effectively be 6 meters squared, and therefore the total magnetic flux inside the coil would be 30 Weber. So we can calculate the total magnetic flux inside a coil by multiplying the flux inside one loop by the number of turns, capital N. We call the total magnetic flux in an area enclosed by a conducting loop the flux linkage.